As you may remember, we are trying to solve this problem, this equation, for the vector x. A is a matrix, x is a vector, and y is a vector. I want to solve for x. So we're going to start with the simplest cases. Well, actually, the very simplest case is A is the identity matrix, and we're done. But it'll be a little more complicated than that. So in this case, we'll have A is n by n, so it's square, and symmetric, or for complex entries or matrices, it would be Hermitian. So this is our simple case. Let's take a look at what this gives us. Start with the definition. If A is real valued, then we call it symmetric. If A transpose is equal to A. And we could also write it this way: A m comma n is equal to A n comma n for all m and n in the list 1 through n. So nice simple example: 1, 3, 7, 3, 7, minus 5, minus 2, 6, minus 2. Next definition. In this case, if it's complex valued, we call it Hermitian. If A, H is equal to A, and for this case, it's just as before with the transpose A n comma m. A m n is equal to A n m, but in this case conjugated. So an example of Hermitian might be 1, 3 plus j2, 1 minus j3, this would be 3 minus j2, minus 5, minus 6. Notice the diagonals have to be real because they have to be their own conjugates. So eventually, we will work up to non-symmetric and non-square. So we'll start though with a tool that's going to be very, very valuable and useful to us. And those are eigenvalue decompositions. So, and it turns out that eigenvalue decompositions of symmetric and Hermitian matrices turn out to have some nice properties. Okay, so an eigenvector of an n by n matrix is a vector V such that A V is equal to lambda V. For some complex scalar, lambda, and the scalar lambda is called an eigenvector associated with V. Okay, so we've got eigenvectors, eigenvalues, symmetric matrices. We're ready to go on to the next step. So how do we find eigenvalues and eigenvectors? We will actually later talk about some computational ways of doing this. But for now, we know that this equation must hold. So we can use this in order for this to hold for non-zero vector V, it must have a determinant of 0. So we want the determinant of A minus lambda I equal to 0. In other words, it must have a non-trivial null space. We must be able to multiply it by some vector and it comes out 0. So the determinant here gives the evaluates to some polynomial equation because we have that equation in lambda, and setting that equal to 0 is what we call the characteristic equation. So that is determinant of A minus lambda I is equal to 0. gives the eigenvalue, lambda. There's another way that I actually prefer for getting the eigenvalue and the associated eigenvectors, and that is this really useful way. MATLAB use the eig command, and it'll give you multiple outputs if you select that option, to give you both the eigenvectors and the eigenvalues. So one of the main features of the very early versions of MATLAB was that it provided an interface to linear algebra code that could robustly find matrix inverses, multiply matrices, and find the eigenvalues and other types of decompositions. So this is really at the core of it, and it was built on code that was written and funded by DARPA for doing robust computational mathematics. So that's the general idea. We have to solve that polynomial equation, and coming up with it is bad enough. If you have a 2 by 2 matrix, it's something that you can attempt on your own. If you have a 30 by 30 matrix, it's really hard to do. So that's why we use software packages to do it. Okay, so we've talked about what an eigenvalue is and what its associated eigenvector. So now let's branch out to a full eigenvalue decomposition. So we're assuming that the matrix A has n linearly independent eigenvectors, which we will call v1 up to vn. Well, because of this, we know that A times v1 is just going to be, now these may each have their own individual eigenvalues, very likely the case. So by definition, we're going to have something like this. Well, this can be written as this set of equations here as matrix equations that look like this. We have A times these vectors here. They're column vectors, so I'm just going to throw them in there and accentuate their column nature, like so. And that's just equal to that same set. There, identically the same set times this matrix here, lambda 1, lambda 2, up to lambda n, a diagonal matrix. So this matrix here we'll call V, and for this matrix we'll use a capital lambda, giving us the expression or the matrix equation AV is equal to V lambda. Okay, so we've already stated it above, but I'm going to put it here explicitly. If the i's are linearly independent, then we get A is equal to V lambda V inverse, or equivalently we could solve for lambda as V inverse A V. Okay, so this is not true for all matrices. Even if the V's are linearly independent, it only works for symmetric matrices. As noted above. So this comes from the Schur triangularity lemma, which is that any n by n matrix is unitarily similar to an upper triangular matrix. So that's any n by n matrix, and that is for any given. In fact, let me pause this and I'll just put the text here for you. Okay, so here's the basic Schur triangularity lemma. We'll go into actually showing it because it's useful to see where this comes from. It says that any n by n matrix is unitarily similar to an upper triangular matrix. That is, so if you have some matrix B that's n by n, there is an orthogonal matrix V such that B is equal to V times this upper triangular matrix delta times V Hermitian. So where does this come from? It comes from the basic fact that you can do row and column operations and Gaussian elimination to turn a matrix into an upper triangular matrix. And those operations can be combined as a product of simple unitary matrices and giving you a unitary matrix. But let's look more into detail. If that doesn't make sense yet, that's okay, because we're going to look into this in a little more detail and see how it plays out in practice. But yeah, let's do this. Diagonalization. So let's take a look at this. If B is Hermitian, then B